Welcome back, students. Let's do the exercise problems in this lesson, and I will start with problem 6.2, not with 6.1, because I believe that with the inputs that you've got to reason how the current will flow in those circuits, you will be able to do those problems. Even if you're not able to, then at least you spend some time and then figure things out. Let's look at exercise problem 6.2. It says use Lenz's law to determine the direction of induced current in the situations described by figure 6.19. A wire of irregular shape turning into a circular shape. And then B, a circular loop being deformed into a narrow straight wire. Okay, so let me take up the first case. This is 6.2. So what it says is that you have a magnetic field that is going into it like this, into the board. And then you have an irregular shape, a loop of irregular shape here, a wire of irregular shape. So it's something like this. I'm doing it approximately, something like this. So you have A here, and then you call this point as B, and then C, and then D. This is what you call the different points on this irregular shaped wire. So this is turning into a circle. So how will it turn into a circle? You need to stretch it like this, so that these arrows denote that. You have to stretch this in such a way that this irregular shaped wire will become a circle. So you need to find out in which direction the current will flow. Okay? Clearly, as it is from a narrow strip, as it is increasing, as it is becoming a circle, the area of this wire increases. If the area increases, then the flux through it also will increase. The flux through the loop will also increase. So the flux through the loop changes, then an EMF must be generated. If an EMF is generated, then you need to find the direction in which current will be sent through this wire. It's a closed loop, so current can flow through that loop. Okay, so that's the question. Let's see. As it is expanding, the flux is increasing. So what should you do? Or what should the current do? The current should oppose the change. It is increasing, so it should decrease. Okay, which flux should it decrease? The flux which is going into the board. So the flux is going into the board, and that is increasing as this wire expands. So that has to be reduced. If that has to be reduced, then I need to put the flux in this direction. If I need to put the flux in this direction, then the current should flow like this. So the direction of the current would be, if I take A as a starting point, A, D, C, B. A to D to C to B to A again. Okay. So this is the direction of the current that is flowing into this. Okay. What's the second one? The second one is a circular loop being deformed into a narrow straight wire. And in this case, the magnetic field is in the opposite direction. So this is A, and if I take B, it's coming out, the field is coming out. In the first case, the field lines are going in, now the lines are coming out. You see the arrow here. So here you have a circular coil, and it is becoming, you're constricting it, you're changing the shape, you're deforming it in such a way that it becomes a thin wire like this. Okay, you can clearly see that as I press this, the area is reducing. If the area is reducing, then the flux through this loop is changing. If the flux through that loop is changing, an EMF will be induced. If an EMF is to be induced, if an EMF is induced, then because it's a closed loop, then current will flow in it. And in which direction will the current flow? The current will flow in the direction such that it produces a magnetic field that will oppose the change in the flux. Okay. So now the flux is this way, and it is reducing. If it reduces, then I should put the flux in the same direction. I need to increase it. The current has to increase it. So the flux is in this direction. So the current also should put the flux in this direction, because the flux is reducing. So the current should oppose that change. So it has to put flux in this direction. It has increased the flux. So if it has to increase the flux, then current should be flowing in this direction, because the flux is in this direction. Okay, so if we see this, which is A, which is B. So this is A, and this is B, and this point is C, and this point is D. Okay, and it gets constricted. So we are constricting it. We're pressing it so that it becomes a wire. Okay. So which direction I said? The current will flow in this direction. The flux should be in this direction. So this is the direction. So if you start from A, then you go from A to D and to C to B, and from B to E. So this will be the direction. In both cases, the direction is the same, but you have to understand that in the first case, this is the flux is increasing, and this flux is into the board. But in the second case, the flux is out of the board, but it is decreasing. So that is why you end up having the same result, the same direction for both cases. Suppose I had the field in the same direction as this. If I had crosses instead of dots, then when I do this, then the current will flow in the opposite direction. You go from A to B to C to D to E. You can verify that yourself. So this is how you do 6.2. And problem 6.3. A long solenoid with 15 turns per centimeter has a small loop of area 2 centimeters squared placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 amperes to 4 amperes in 0.1 second, then what is the induced EMF in the loop while the current is changing? Okay, so you have a long solenoid. I'm going to use blue for that. This problem 6.3. let me have a long solenoid. Okay, so there will be some current I flowing through that. And what they say is that inside the solenoid you have a small loop. So this is the axis, okay, and you have a small loop, small coil, and that is also aligned with the axis. It's perpendicular. The plane is perpendicular to the axis of this solenoid. So if you have a big solenoid like that, then you have a small coil like this, okay, like that. I don't know. Hope you are able to see this. So it's like this. They are aligned inside. Now, so this solenoid, if you talk about the solenoid, then the solenoid has an N, which is number of turns per unit length of 15 turns per centimeter. So this is 15 turns per centimeter, which means that if you have 15 turns per centimeter, then you will have 1500 turns per meter. Clearly, I am converting that into turns per meter. So if it is 15 turns per centimeter, then 1 meter you have 100 centimeters, so you will have 1500 turns per meter. That's N. And second point is that the area of this loop, the area of this small loop is 2 centimeters. The area of the loop, I'll just put small a because it's for the small loop. So this is the area. I'm talking about this area, not this area. I'm talking about this area for the loop. That is 2 centimeters squared. So it is 2.0 centimeters squared, meaning 2.0 into 10 to the power minus 4 meters squared. I am converting them all into SI units. And the current carried by the solenoid changes steadily from 2 amperes to 4 amperes in 0.1 second. Okay. So the current I, it changes from 2 to 4 amperes in 0.1 second. Then what is induced EMF in the loop while the current is changing? Obviously, if the current has stopped changing, no EMF will be produced. But if the current, okay, this is I call it as I, so take it as I, capital. So this is the current, this is the solenoid. Okay, so this current will set up a field there, and that field B will send, there will be magnetic flux through this loop also. If that changes, then the number of, the magnetic flux through this loop changes, there will be an EMF induced. So that's what we're going to find out now. Okay. First, what do you need? To find the EMF induced, you need to know the flux, right? What is the equation? Minus N d phi b by dt. So I need to know the flux. But to know the flux, I need to know the field strength. What is my flux? Say my flux phi is equal to B, which is a magnetic field set up by this field strength set up by this current in the solenoid, into this area, this small area. So I am talking about only this area, not the whole area, because that is the solenoid. We bother only about this particular loop. So it's B. So what is B now? B, from your long solenoid equation, mu naught N into I. Okay, source of phi b. If magnetic flux phi b is equal to mu naught n I into A. Okay, so let me plug all those things here. So here it's going to be equal to minus n d by dt of mu naught n I to A. Okay, let me take all the constants out because mu naught is a constant. It's not going to change. N, the number of turns per meter of the solenoid, also is not going to change. Then area of this coil, that small loop, that is also not going to change. Then only current is changing. So I can take all those things out. So I get this is equal to minus n mu naught n A to d I by dt. Okay. Now I need to put in the numbers. What is n? The number of turns of what? The solenoid? No. It's the number of turns of this loop. How many turns? Just one. Right? So I get to unit minus 1. And mu naught, you know, that is 4 pi to 10 power minus 7. And this n is 1500 multiplied by the area of this coil is 2 into 10 power minus 4 and di by dt. So the rate of change of current. So di by dt. How do you di by dt? So di by dt is delta I by delta t because it's constantly changing. So you are going from 2 to 4. So the final is 4, initial is 2, so 4 minus 2 amperes, and the time you take to do it is 0.1 seconds. Okay. di by dt is also equal to delta I by delta t because it is changing at a constant rate. If it is not changing at a constant rate, then you need to find di by dt at every instant, but that is different. But since it is changing, the current is changing at a constant rate, I can do delta I by delta t. That will be equal to my di by dt. Anyway, so when I do this, what I'm going to get? This I can take as a 10 power minus 1, you know, 0.1, so I can adjust stuff now. So this is going to be equal to, this is 2, I'm going to get 2, then 4, then 4 pi, okay, 4 into this 4 into this, like 1500, I'm going to write it as 1.5 into 10 power 3. Okay, and then handle this, and then handle this, and all of this. Then this 0.1, 10 power minus 1, when it comes there, it can be 10. I get that, and into pi into 10 power minus 7 into 10 power minus 4. Okay, so 10 power 3, 10 power 1, so I can remove this. So I got 10 power minus 7, and this is 4 into 1.5 is 6. 6 into 4 is 24. 24 into 3.14 to 10 power minus 7 volts. So that's 3 times, that is 74 24 into 3.14, so somewhere around 75, right? It's more like that. So 75, approximately 75 10 power minus 7 volts, or is also equal to 7.5. Let me have a negative sign. Minus 7.5 into 10 power minus 6 volts. So this is the EMF induced in that small loop. So very, very small. The EMF induced is very small, but then there is an EMF induced because of this change in current. Let's look at problem 6.4. A rectangular wire loop of sides 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 cm per second in a direction normal to the longer side and to the shorter side of the loop? For how long does the induced voltage last in each case? Okay, so it's like this. Problem 6.4. So this is a magnetic field. Let me assume that it's going into the board. And you have a rectangular loop. So the dimensions are given. One side is 8 cm and the other side is 2 cm, 8 by 2 cm square loop, and it has a very small cut. So it's open, meaning that no current is going to flow through it. But the EMF will be generated, so no current will flow through it. Anyway, so that's what it means. Let us suppose that I have that like this. There's a small cut, meaning that this is open here. So, whatever voltage is getting induced will be available here. That's what it means. Okay, so this is 2 centimeters. I'll call this as this is breadth B and this is length L. Okay, the length is 8 centimeters. Length is 8 centimeters, and then the breadth is 2 centimeters. And the magnetic field B is equal to 0.3 Tesla. This is 0.3 Tesla. And this is getting pulled out of the loop with the speed of 1 centimeter per second. V is equal to 1 centimeter per second. So now they want you to find the EMF induced in them, in this loop. Okay? When it is done this way, and the next is, if you, instead of keeping it like this, if you keep it vertically. Now the loop is like this. Instead of that, if you keep this vertically and if you move it out with the same speed, then what would be the EMF induced? Same loop, but the first case you are moving it like this, second case you are moving it like this. Okay. That's what you do. Okay. So, okay, let's see. When I move it like this, what is going to happen? Clearly, the flux through it is changing. If the flux through it is changing, then an EMF will be induced. As long as it is inside the magnetic field, even if you move it, no EMF will be induced because there is no flux change as long as it is inside the field. But at the moment you start taking it out of the field, then the flux in it is changing. Okay, let's see. So what's the flux now? The flux now is initial, like before it just gets out of it. So the flux now is phi b is B, capital B, into L times B. Okay, and then its area. That's the flux now. As I take it out, the flux is going to change. So that is my initial flux. At any point in time, there would be a change in the flux as I take it out. Suppose I got it like this. Like this. Okay? Now, you see, I call this as X. When it is like this, then what is the flux inside? The flux has changed, you can see that. The flux is now less than it was before. So now, phi b, that at some distance x, I'm not going to call it as final. Final will be 0 because you won't take it completely out, then that will be 0. But at some distance x, the flux is going to be equal to same b and then same small b, but now you don't have small L. Now you have L minus x. Okay. So that is your flux when you are here, which means that what's the change in flux? I'll say delta phi. Delta phi b is equal to delta bx, which is final right now, minus delta phi bx minus phi bi. Sorry about that. So this will give me b L minus x minus b L b. So what I'm going to get now? So this and this will cancel and I will be left with b x minus. That's the change. And this change would have taken some time. There would be delta t. There would be delta t. There will be delta t for that. So what is the change in flux now? The rate of change of flux. So what is my delta phi b by delta t, which is also equal to d phi b by dt, because I am taking it with a constant speed. It is changing constantly. The flux inside is changing constantly. So delta phi b by delta t is equal to d phi b by dt. So that is going to be minus bx, and then this delta t is the time it has taken to go from here to here. So I just put some time t there. Okay. So what I'm going to get now? So this is going to be minus bb and then x by t. What is x by t? It's actually velocity. Because if you are moving, you have covered x distance in t time, then x by t must be v. So this is minus bb v. Okay. And what's the EMF induced? The EMF induced is actually minus of d phi b by dt, and that would be b v. Okay. So if I plug in these values, then I must be getting, what is B? B is 0.3. And then what is my B? That is 2 centimeters. Okay. So I'll say 2 into 10 power minus 2 meters. Then multiplied by, what is my velocity? 1 centimeter per second. Which means it is 10 power minus 2 meter per second. That's the velocity now. So what I'm going to get now? So my induced EMF is going to be 0.6 into 10 power minus 4 volts. When I move it like that. I can use the same logic for the other case also. When I, instead of moving it like this, if I move it like that, now this is for case 1, right? This is for case 1. Okay. This is for case 1. Then case 2, they move it like that, then what is going to happen? I'll get the same E, epsilon, but then instead of B, B, V, now this would be the long side and that would be the short side. So I'll get B, L, and then V. Because you'll still be pulling it with the same speed, but then you keep it vertically and then move it like that. In that case, you notice that a lot of flux will change in the same time. Notice it. A lot of flux will change in the same time. If you're moving it like this, then certain amount of flux is changing. Okay? But now if you're moving it like this, you see when it is out, then a lot of flux change is happening. So this should be greater. Okay? So that's intuitively you should know. Then mathematically, this B will become L. That's all. And the rest will be the same. So you are going to have 0.3 into, instead of 2, I am going to have 8. 8 into 10 power minus 2. And V will be the same, 10 power minus 2 meters per second. And in this case, my E is going to be equal to 2.4 to 10 power minus 4 volts. Okay, hope this is clear to you. Problem 6.5 is very easy, the straightforward application of the formula. Let me read the problem first. A 1 meter long metallic rod is rotated with an angular frequency of 400 radians per second about an axis normal to the rod passing through its one end. The other end of the rod is in contact with the circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Calculate the EMF developed between the center and the ring. This is the same problem that you did as an example problem. Example I pressed is example 6.6. So this is the problem that you did. So we're going to make use of the same thing. So it says that exercise 6.5 is, so you have a rod and then it is rotating, excuse me for my drawing, in a circular ring, and there is this magnetic field which is going into it. Okay, so that. So they want you to find this rod, this is going around it. Then they want you to find the EMF induced between this end and this end. Okay, so we already derived this expression. We said the EMF induced is equal to B omega r squared by 2. When B is the field strength, it has to be 4. Okay. So B is the field strength and omega is the angular velocity of this rod. Then r is this radius, which is actually the length. This is r. If it is 1 meter length, then that is what it is by 2. So that's very easy to do. So it's straightforward application. This E is equal to B is 0.5 Tesla. So you get 0.5, and then omega is 400 radians per second. Okay, and then r is 1 meter long, so it's going to be 1 square, and then we're going to do 2. Okay. So clearly this is 1 and this will be 200 into 0.5, it's going to be 100 volts. So the potential difference between this point and this point would be 100 volts. It's a very straightforward problem. Okay, then let's move on to do problem 6.6. A circular coil of radius 8 centimeter and 20 turns is rotated about its vertical diameter with an angular speed of 50 radians per second in a uniform horizontal magnetic field of magnitude 3 into 10 power minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. If the coil forms a closed loop of resistance 10 ohms, then calculate the maximum value of current in the coil. Then calculate the average power loss due to joule heating. Where does this power come from? Okay. Anyway, a part of this problem you cannot do because we have not taught you that, particularly the last part. Calculate the average power loss due to joule heating. And where does this power come from? That part, where does the power come from? That can be answered. But calculating the average power loss cannot be done now because you need to wait for the next lesson to do this, that part. But the rest can be done. So you have a circular coil of radius 8 centimeter and 20 turns. It's rotated about its vertical axis. It's like this. So you have a circular coil. Okay, and this is the vertical diameter. So it's rotated about its vertical diameter. And in a magnetic field of magnitude 3 into 10 power minus 2 Tesla. So let's say there is a field. Okay. So now you need to find the EMF induced. But it's like you can see that it's the AC generator. It's like you have two poles, north and south, and then you have a coil inside that. It's like that. So the pole is here, the north pole is here, the south pole is on the other side. So you have a loop here, and then the field lines are going in, and now you are rotating that loop, that coil. And clearly the flux through the coil will be changing. So because the flux through the coil is changing, and there will be an EMF induced in the coil. So it's AC generated. Okay. They've given you this too. Omega is also given. So what are the things which are given? Radius is given. Radius of the coil is 8 centimeters. So 8 into 10 power minus 2 meters. It's given. Radius is given. The number of turns, N, is 20. And omega is 50 radians per second. 50 radians per second. And B is 3 into 10 power minus 2. Minus 2 Tesla. So what is the EMF induced? We know this. The EMF induced E is equal to NBAW sine omega t. Okay? This is from the AC generator part of this lesson. Apply the value straight away, then you will get the answer. Okay, so what is N? N is going to be 20, and then B is 3 into 10 power minus 2, and then area is going to be pi into r squared, 8 into 10 power minus 2 the whole square, and omega is 50 and sine omega t. Okay. So if I do this, this is going to be 20 into 50, so that would be 1000. Let me do this. Okay, so this is going to be, let's say 3 into pi into 64 into 1000, this one, 1000 into 10 power minus 2 into 10 power minus 4. 10 power minus 4 here, 10 power minus 2 here, 10 power minus 6, so we are going to get 10 power minus 3 out of this, right? So this is going to be 3 into pi to 64, so 10 power minus 3. So we said that pi squared is roughly 10, so 3 into pi is approximately 10. So 10 into approximate, I'm giving an approximate value because I'm not going to do the exact calculation. This is roughly 10. So 640 into 10 power minus 3. So, and that will give you again 0.64 or something, 0.64 volts. Okay. So that's the EMF induced in this coil of 20 turns. And the resistance is also given. That if the coil forms a closed loop of resistance 10 ohms, so you have a closed loop with resistance 10 ohms, then clearly the current would be flowing in that coil. So the current can be given as by R, so 0.64 divided by R is 10 ohms, so that will give you 0.06 approximately. Okay, this is all approximate. Okay, so that's it. This is approximately this, and this is approximately 0.06 amperes. So that's the current response. And this obviously is AC. Okay, AC. So you will have like this. Okay, this is your voltage maximum. This is your minimum. So what's the average? This is for one cycle. But what's the average for one cycle? You know, half of the cycle is positive, half of the cycle is negative. So on the average, it will be 0. Okay. By the way, so this is actually, I forgot that, sine omega t. Okay. So you'll also get sine omega t. But the maximum, okay, this is maximum will be when this is 1. So that is when you get 0.64. Okay. For all the, at every other time, then you will get some other value, right? Depending on t, then you will have some value here. Omega is anyway it's 50, so you get 50t. Okay, I can also put that 50t, sine 50t. So depending on the time value, you get some EMF induced at every point in time. The maximum is when this is 1. So the maximum EMF induced is 0.64. So that's how you. And this is also the maximum current. Because the current also will vary depending on the EMF, because it's always EMF by resistance. So if EMF is changing, then this will also change. But now it is the maximum EMF by the resistance. So this is how you do this problem. Okay, now let's do problem 6.7. It's slightly a tricky problem, but you can do it. A horizontal straight wire of 10 meters long extending from east to west is falling with a speed of 5 meters per second at right angles to the horizontal component of the Earth's magnetic field, which is 0.3 × 10 to the minus 4 Weber per meter square at that place. Now, okay, A, what is the instantaneous value of the EMF induced in the wire? Then what is the direction of the EMF? Then which end of the wire is at the higher electric potential? 6.7. So what is the problem? You have a wire, a long wire, 10 meter wire, a rod or something, pretty long, and it is falling. The directions are given. Okay, let's talk about my own case. For me, this is east, and this is west, and this is north. This is my south. So this wire is falling in the, it's kept in the east-west direction, so it's falling like this. Okay. It's falling like this. And the magnetic field, the Earth's magnetic field right now is in this direction, right? So it goes from south to north. The field lines will go from magnetic south to magnetic north. We've explained it why already. Okay, anyway, let's forget that. So the field lines are in this direction. The rod is falling like this. Now what is the EMF induced? That is the question. Okay. Let us, we can do it in two ways, but let me focus on just one. Let me take the Lorentz force view, which is much easier for you to understand. Okay. Okay. So I'll put it this way. So let's suppose that the flux is like this. It's going into the ball. Okay. And the flux is in this direction, so the rod is like this. So the rod or the wire is falling like this. So clearly, what's going to happen? Clearly, there is an EMF that is going to get induced in this. Okay, let's see. Then how do you find that EMF? I said I'm going to use the Lorentz method. Okay? Lorentz motion. It's easier to do. You can also do it in Faraday's method, but this is much more intuitive than that. Okay, so in this case, let's see. This is falling. The rod is falling. And the field is in this direction. That's what I said, from south to north. The field is in this direction, the rod is falling. Which means the free electrons in this rod are also falling in this direction. So QV, or let's say V, the velocity of the electrons in this direction, V cross B is like that, but electrons, so negative charge, so the force acting on the electrons will be in this direction, minus, right? So you know that F is equal to QV cross B. V is in this direction, B is in this direction, all right. But notice that Q, we are talking about free electrons. So those free electrons will experience a force in this direction. V cross B is this, but that's a positive charge, QV cross B. Because you have negative charge electron, then the force acting on the electron is in the opposite direction, minus. So electrons will be pushed towards west. I told you this is my east, west. And this side would be more positive than this side. Because free electrons are getting pushed towards west, as we just explained. So you can easily say that in this case, okay, this is my south and that's my north. We're talking about Earth magnetic field, so it's like that, and it's going down. And the electrons, so V cross B, like that, electrons will be pushed in this direction. Okay, electrons will be pushed here, electron will be negative, and this will be positive. But I told you, this is my north, this is my south, and that is my north in this picture. Because field lines are going into the board, which means they go from south to north, right? So this is my south, and on the other side is north. Okay? So if this is my south and that is north, and this must be east and this must be west. So this is east and this is west. Okay? So you can see that on the eastern side we are positive, and on the western side it's going to be negative. So that you can easily answer. Okay? And you know that estimates is speed. And what is EMF induced? You know the EMF induced, right? You already done that. EMF is equal to BLV. So this can be taken to be what? Can be taken to be B is 0.3. 0.3 into 10 power minus 4, and then length is 10 meters and velocity is 5 meters per second. So if you do that, so it will be 3 into 5, 15, 10 power minus 4, so that will be 1.5 into 10 power minus 3 volt. So you will have an EMF of 1.5 millivolt. The potential difference of 1.5 millivolt at the two ends of this wire. So just take a wire, drop it, take a 10 meter wire, just drop it, and you can measure a potential difference of 1.5 millivolt like this. Okay, hope this is clear to you. On 6.8, current in a circuit falls from 5 amperes to 0 amperes in 0.1 second. If an average EMF of 200 volt is induced, give an estimate of the self-inductance of the circuit. Okay. So now we're talking about self-inductance, right? 6.8. So what is given? The current is falling. So current I is falling from 5 to 0 in 0.1 second. So 5 to 0 amperes in 0.1 second. Okay. And what is this? And if an average EMF of 200 volts is induced, so if this induces an EMF, the back EMF of 200 volts, then they ask you to find the inductance. So what do you know? E is equal to N minus n d phi by dt, and that is also equal to minus L di by dt. Okay? If I'm going to just take the magnitude only, okay, I can even just go ahead with whatever is there, but let's see. But finally, what we're interested in is the magnitude. So this is 200 volts, and is equal to minus L di. How much has it changed? It has changed from 5 to 0. So your final is 0, initial is 5, and divided by what time has it taken? It has taken 0.1 seconds. So that gives you 5 by 0.1, so that which will be 50 L. Okay, so L is going to be equal to 200 by 50, 200 by 50 into 4 Henry. Okay, it's very easy to do. But you see, when you apply this equation, sometimes you get a negative number too. It doesn't matter. In this case, the EMF is given as 200. Okay, if they have given you minus 200, then you have to do it. You have to ignore this the negative sign. Basically, what is important is the magnitude, because whether it is increasing from 0 to 5 or this is minus 200, it doesn't matter. Ultimately, the magnitude is what you need. Okay, so this is how you do this problem. 6.9. A pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current in one coil changes from 0 to 20 amperes in 0.5 seconds, then what is the change of flux linkage with the other coil? Okay. So 6.9. So they have two adjacent coils, and there is current flowing in one coil. Okay. This is very whatever. Okay. Changes from 0 to 20 amperes in 5 seconds. So this current I, okay, this changes, I changes from 0 to 20 amperes in 5 seconds. I'll put time. Okay, this delta I is this. Delta I is 0 to 20 amperes. And delta T is 0.5 seconds. 0.5 seconds. Okay. And they want you to find the change of flux linkage. The change of flux linkage. They want you to find the change of flux linkage. Change of flux linkage. Okay. What is flux linkage? So flux linkage is equal to N into phi b. So this phi b is the flux. It gives you a measure of magnetic lines which are going through a particular area. That is phi b. And if you have multiple loops, then this flux will go through all those loops. So the flux linkage is a measure of the flux which is linking all these loops. So phi b into N is the flux linkage. But they don't want you to find that. They want you to find the change of flux linkage. Okay? So what do you know? We know that EMF is equal to minus N d phi by dt. So this is actually the change of flux linkage, N d phi. That's a change, right? If phi b changes, then N phi b will also change. So the change of flux linkage is N d phi by dt. And what else do we know? We also know that this is equal to minus M, the mutual inductance, okay, into d I of the first coil, di1, let's say this I1, this will be I2, right, di1 by dt, okay, dt. So if this is a flux linkage, this must be the flux linkage too. Because in the denominator you only have dt. So this is flux linkage and this must be flux linkage. M di is the flux linkage. So the flux linkage or the change in flux linkage, I should have said if this is a change of flux linkage, this must also be the change of flux linkage, the change of flux linkage. Okay. So the change of flux linkage is this, I m di equal to m di or m delta I. Okay. So this must be that. So what is that then? So n delta phi b is equal to what is m? M is given to be 1.5 meters. 1.5 meters. And what is delta I1? How much does it change? It changes from 0 to 20. Okay? So final is 20, initial is 0. So that is the flux linkage. That's the delta I. Okay? And I'm going to get 20, right? So this is going to be 20. So 20 into 1.5 will be 30. So n delta phi b, which is the flux linkage, that is 30 Webers. Delta phi b will be in Webers, delta phi b will also be in Webers, and this is simply a number of turns, so the unit is also Webers. Well, I can go ahead and calculate the EMF induced. That's very easy, right? So if we want to find the EMF, so that's going to be equal to n delta phi b by delta t. So that is 30 by delta t, it is 0.5 seconds, right? So 0.5. So that will give me 60 volts. So the EMF induced would be, I'll say minus, right? It's minus 60 volts. The magnitude would be 60 volts. Minus just tells you which terminal is positive and which other terminal is negative. But otherwise, potential difference is going to be 60 volts between them. So you can find the EMF induced also, but that is not asked in the problem. This is how you do this. Okay, the next problem is problem 610, and that is also the last problem that we will do in this lesson. A jet plane is traveling towards west at a speed of 1800 km per hour. So what is the voltage difference developed between the ends of the wing having a span of 25 meters? If the Earth's magnetic field at the location has a magnitude of 5 into 10 power minus 4 Tesla and the dip angle is 30 degrees. So what are they saying? They're saying that there is a plane which is traveling towards west at a location, and at that location the magnetic field value is also given, and now we are asking you to calculate the EMF induced between the two ends of its wings. That should surprise you first. You probably may not have known that when an airplane flies in air, then there would be a potential difference induced between the two ends of its wings. Because it happens. Why? A plane or its wings, metals, and you have the Earth's magnetic field, and you have a conductor that is moving in the Earth's in a magnetic field. So clearly, Faraday's law of induction must apply to it. So it doesn't matter whether it is a coil or anything else. Even if it is a plane moving in air, you will have that impact. And even us, for example, we move because we ourselves are conductors. Poor conductors, but okay, conductors. Even we will have potential difference between one end and the other end. So that should surprise you. Let's do that problem. So the plane speed is given 1800 km per hour. So you have to convert that into SI units, meter per second. Okay. Then what is the voltage difference developed between the ends of the wing having a span of 25 meters? So the wing span is 25 meters and this plane is traveling towards west. I told you this is my east and this is my west. So the plane is traveling towards west. So if this is a plane, this is going to be its wings. It's traveling towards west now. So there will be a potential difference between this end and this end. Okay? But think about it. The magnetic field of the Earth is going to be in this direction, from south to north. It's Earth's magnetic field, so the direction is opposite. From south to north. And the dip angle is 30 degrees. So this is my south, this is my north. The dip angle is 30 and it's like this. Notice here. So it is like that. It's a magnetic field. It's like this. Okay? So now it is moving in this field. The plane is moving in this field. Look at its wings. You see, if I take this magnetic field, Earth's magnetic field, I can resolve it along two axes, right? Along the horizontal axis and also along the vertical axis. So you have the horizontal component and also the vertical component. So the horizontal component will be like this. Okay? The horizontal component is like this. The velocity is like that. Okay? So the electrons will experience a force either up or down. You see, V, B, V cross B, then you will have a vertical force or a downward force. So there would be a potential difference here itself, the small, this itself. So that potential difference, would be like this. Wings. Potential difference here, potential difference here, potential difference here, potential difference here. Because you see, the horizontal component will cause this, the electrons to move either down or up. Let's say, we'll calculate it now. V is this, B is this, V cross B is down, but then the electrons will go up. Right? Because the force of the electrons will be upwards. So the electrons will come up and then the top part will be negatively charged and then the bottom part will be positively charged. But that's not much, you see, the difference, the distance is not much. That length is not much. Okay? It will be a small voltage, whatever. But if you take this, the vertical component is what is going to produce the potential difference between this and this. Why? Because V, velocity is this way, vertical component is down, so V, this is V, and vertical component is down, so V, B, yes, V cross B, in this direction for positive, so for negative, it's going to be in the other direction, right? So this will, the electrons will start moving here. And this will be positive and this will be negative. And you see there is a long length. So the potential difference will be appreciable here. potential difference due to the horizontal component is negligible, not much. You see, the vertical component will produce a large potential difference. So that is what I want you to calculate. Okay, so we'll ignore the potential difference at the tips themselves, from this part and this part. Suppose this is a tip, this part and this part. It's not much, you can see that. We can ignore that. But that is due to the horizontal component of the magnetic field. But from the tip to tip, which is very long, 25 meters, okay, and that is caused by the vertical component. So we would be focusing on the vertical component of the Earth's magnetic field. Okay? Okay, so this is 610. So suppose this is your B at this place. So it will have a horizontal component and it will also have a vertical component. So this angle is 30 degrees. So this is my BV and this is my BH. I told you BH doesn't make much difference. It's very small. But then BV is appreciable here. Okay. So let's take B. So BE is 5 into 10 power minus 4 Tesla. This is what is given in your book. I doubt it. Okay. This must be 0.5 into 10 power minus 4 Tesla. Because you cannot have an earth magnetic field which is 5 into 10 power minus 4 Tesla. It has to be 0.5. But I'm not going to make the correction. I'll go with this number. Okay? But I doubt this number. B is that, and V is what we need to calculate. So BV is going to be equal to this BE sine 30, right? So sine 30 be 5 and the BE sine 30. So that would be 5 into 10 power minus 4 into 1 by 2. So I'll just keep it like that. Okay. So that's my B just now. And this will be responsible for the potential difference between the two ends of the rings. Okay. So what I'm going to do? My E, the induced EMF, we know when a conductor moves, in a magnetic field, constant magnetic field, is given by B, L into V. Okay. Now I need to convert this V because the velocity of the speed is given to be 1800 km per hour. So that is actually equal to 1800. If you need to convert that into meter per second, then I need to multiply that by 5 and divide it by 80 meter per second. So this will be 500 meter per second. So the speed is either 1800 km per hour or 500 meter per second. So we got B, we got V, and L you know to be 25 meters. Now it's merely a question of taking these numbers, plugging those numbers in this equation and finding the answer. So E is equal to B is 5 into 10 power minus 4 by 2 into length is 25 into the speed is 500 meters per second. So this 5, I'll take it slightly differently. Okay. So 10 power 2, 5 and 10 power 2 is what I'm going to write. So 5 into 25 into 5 into 10 power 2 into 10 power minus 4 by 2. So this is 5 25 into 25, 625 into, this would be 10 power 2, 10 power minus 4, 10 power minus 2 by 2. And this is 6.25 into 10 power 2, so I can cancel that. Okay. So it will be 6.25 by 2, so that would be 3.125 volts. Okay, so we will do 3.125 volts. So that is the EMF induced between the two ends of the plane. I doubt this. As I said, it has to be 0.5 × 10⁻⁴ Tesla. So in that case, I'll get 0.3125 volt. So that should be the actual 0.3 volt. Not much, 0.3 volt difference. But 3.125, I don't think that's the answer, because this number I feel is wrong. Otherwise, I'm fine with it. Okay? So this is how you do these problems. Hope they're clear to you. And if you have any questions, doubts, particularly in problem 1, which we have not done, you let me know. But the problem 1 we have not done because 6.1, I mean, we have not done because it's a very easy problem to do. Like, it's just, you just need to find the direction. So if you employ the method I gave you to find the direction of the current flowing in an induced EMF circuit, then you can easily do them. If you have any questions, let me know. Thank you.